School of Management Studies IGNOU presents an audiobook on the course MMPC 005 Quantitative Analysis for Managerial Applications for MBA program. Block 3 Sampling and Sampling Distributions. Unit 12 Chi-square Tests.
After completing this unit, you should be able to appreciate the role of the chi-square distribution in testing of hypotheses, design and conduct tests concerning the variance of a normal population, perform tests regarding equality of variances from two normal populations, have an intuitive understanding of the concept of the chi-square statistic, use the chi-square statistic in developing and conducting tests of goodness of fit, and tests concerning independence of categorized data. Introduction. In the previous unit, you have studied the meaning of testing of hypotheses and also how some of these tests concerning the means and the proportions of one or two populations could be designed and conducted. But in real life, one is not always concerned with the mean and the proportion alone, nor is one always interested in only one or two populations. A marketing manager may want to test if there is any significant difference in the proportion of high-income households where his brand of soap is preferred in North, South, East, West, and Central India. In such a situation, the marketing manager is interested in testing the equality of proportions among 5 different populations. Similarly, a quality control manager may be interested in testing the variability of a manufacturing process after some major modifications were carried out on the machinery, vis-a-vis the variability before such modifications. The methods that we are going to introduce and discuss in this unit will help us in the kind of situations mentioned so far as well as in many other types of situations. Earlier, while testing the equality of means of two populations based on small independent samples, we had assumed that both the populations had the same variance and, if at all, their means alone were different. If required, the equality of variances could be tested by using methods to be discussed in this unit. In many of our earlier tests, we had assumed that the population distribution was normal. It should be possible for us to test if the population distribution is really normal based on the evidence provided by a sample. Similarly, in another situation, it should be possible for us to test whether the population distribution is Poisson, exponential, or any other known distribution. Finally, the procedures to be discussed in this unit also allows us to test if two variables are independent when the data is only categorized. We may, for instance, like to test whether consumer performance for a brand and income level are independent. That is, the variables, for example, the sex of respondents, have been measured only grouping respondents in categories. The common thread running through all the diverse situations mentioned here is the chi-square distribution. We start with the recapitulation of the chi-square distribution before we start with the statistical test. The chi-square distribution, a recapitulation. A chi-square distribution is known by its only parameter, viz. The degrees of freedom. If x is a random variable having a standard normal distribution, then x square will have a chi-square distribution with 1 degree of freedom. If y1 and y2 are independent random variables having chi-square distributions with v1 and v2 degrees of freedom respectively, then y1 plus y2 will have a chi-square distribution with v1 plus v2 degrees of freedom. If x square is a random variable having a chi-square distribution with v degrees of freedom, then x square can assume only non-negative values. Also, the expectation and the variance of x square is known in terms of its degrees of freedom. Testing of population variance. Many times we are interested in knowing if the variance of a population is different from or has changed from a known value. Such tests can be easily conducted if the population distribution is known to be or can be assumed to be normal. We shall develop and use the test procedures under different null and alternative hypotheses. One-tailed test. The specifications for the surface hardness of a composite metal sheet require that the surface hardness be uniform to the extent that the standard deviation should not exceed 0.50. A small random sample of sheets is selected from each shipment and the shipment is rejected if the sample variance is found to be too large. However, a shipment can be rejected only when there is an overwhelming evidence against it. The sample variance from a sample of 9 sheets worked out to 0.32. Should this shipment be rejected at a significance level of 5%? It is clear that in absence of a strong evidence against it, the shipment should be accepted. Two-tailed tests of variance. We have earlier used both one-tailed and two-tailed tests while discussing tests concerning population means and proportions. Similarly, depending on the situation, one may have to use a two-tailed test while testing for population variance. The surface hardness of composite metal sheets is known to have a variance of 0.40. For a shipment just received, the sample variance from a random sample of 9 sheets worked out to 0.22. Is it right to conclude that this shipment has a variance different from 0.40 if the significance level used is 0.05? We shall reject the null hypothesis if the observed value of the test statistic is too small or too large. As the significance level of the test is 0.05, the probability of rejecting H0 when H0 is true is 0.05. In this case, the null hypothesis cannot be rejected, and so we conclude that at a significance level of 0.05, there is not enough evidence to say that the variance of the shipment just received is different from 0.40. Testing of equality of two population variances. In many situations, we might be interested in comparing the variances of the populations to see whether one is larger than the other or they are equal. For example, while testing the difference of means of two populations based on small independent samples, we had assumed that both the populations had the same variance. We may want to test if it is reasonable to assume that the two population variances are equal. While testing the equality of two population means, the test statistic used was the difference in two sample means. As we shall discover soon, while testing the equality of two population variances, the test statistic would be the ratio of the two sample variances. The F distribution. If xi and x2 are independent random variables having chi-square distributions with v1 and v2 degrees of freedom, then y equals to x1 over v1 divided by x2 over v2, which means it has an F distribution with vi and v2 degrees of freedom. The F distribution is also tabulated extensively and finds a lot of applications in applied statistics. An F distribution has two parameters. The first parameter refers to the degree of freedom of the numerator chi-square random variable, and the second parameter refers to the degrees of freedom of the denominator chi-square random variable. The right tail of various F distributions with different numerator and denominator degrees of freedom is extensively tabulated. The left tail of any F distribution can be easily calculated by some simple modifications. Being a ratio of two chi-square variables and their degrees of freedom, an F distribution exists for only positive values of the random variable. It is symmetric and unimodal. A one-tailed test of two variances. A purchase manager wanted to test if the variance of prices of unbranded bowls was higher than the variance of prices of branded bowls. He needed strong evidence before he could conclude that the variance of prices of unbranded bowls was higher than the variance of prices of a branded bowl. He obtained price quotations from various stores and found that the sample variance of prices of unbranded bowls from 13 stores was 27.5. Similarly, the sample variance of prices of a certain brand of bowls from 9 stores was 11.2. What can the purchase manager conclude at a significance level? Let us use the subscript 1 for the population of prices of unbranded bowls and the subscript 2 for the population of prices of the given brand of bowls. We also assume that both these populations are normal. The purchase manager would conclude that the unbranded bowls have a higher price variance only when there was a strong evidence for it and not otherwise. A two-tailed test of two variances. A two-tailed test of equality of two variances is similar to the one-tailed test discussed in the previous section. The only difference is that the critical region would now be split into two parts under both the tails of the F distribution. Let us take up the decision problem faced by the marketing manager, but with some slightly different figures. Here the marketing manager wanted to know if display at point of purchase helped in increasing sales. He picked up 13 retail shops with no display and found that the weekly sale in these shops had a mean of Rs 6,000 and a standard deviation of Rs 1,004. Similarly, he picked up a second sample of 11 retail shops with display at point of purchase and found that the weekly sale in these shops had a mean of Rs 6,500 and a standard deviation of Rs 1,200. If he knew that the weekly sale in shops followed normal distributions, could he reasonably assume that the variances of weekly sale in shops with and without display were equal if he used a significance level of 0.10? In the previous section, we developed a test procedure based on the assumption that variance 1 is equal to variance 2. Now we are interested in testing if that assumption is sustainable or not. We take the position that unless and until the evidence from the samples is strongly to the contrary, we would believe that the two populations, viz. Of shops without display and of shops with display, have equal variances. Testing the goodness of fit. Many times we are interested in knowing if it is reasonable to assume that the population distribution is normal, Poisson, uniform, or any other known distribution. Again, the conclusion is to be based on the evidence produced by a sample. Such a procedure is developed to test how close is the fit between the observed data and the distribution assumed. These tests are also based on the chi-square statistic, and we shall first provide a little background before such tests are taken up for detailed discussion. The chi-square statistic. Let us define a multinomial experiment which can be readily available as an extension of the binomial experiment introduced in the previous unit. The experiment consists of making n trials. The trials are independent and the outcome of each trial falls into one of k categories. The probability that the outcome of any trial falls in a particular category, say category I, is Pi, and this probability remains the same from one trial to another. Let us denote the number of trials in which the outcome falls in category I by n1. As the total number of trials is n and there are k categories in all, obviously n1 plus n2 plus till nk is equal to n. Each one of the n s is a random variable and their values depend on the outcome of n successive trials. Extending the concept from a binomial distribution, it is not difficult to understand that the expected number of trials in which the outcome falls in category I would be E in brackets Ni is equal to N dot Pi, where I is equal to 1, 2, 3 till K. Using the concepts developed so far, it is not difficult to understand how a test procedure can be developed and used to test if the data observed came from any known distribution. The degrees of freedom for the chi-square statistic would be equal to the number of categories, that is K minus 1 minus the number of independent parameters of the distribution estimated from the data itself. If we want to test whether it is reasonable to assume that an observed sample came from a normal population, we may have to estimate the mean and the variance of the normal distribution first. We would categorize the observed data into an appropriate number of classes, and for each class, we would then calculate the probability that the random variable belonged to this class if the population distribution were normal. Then, we would repeat the computations, calculating the expected frequency in each class. Finally, the value of chi-square statistic would have K minus 3 degree of freedom since two parameters, the mean and the variance of the population, were estimated from the sample. Testing independence of categorized data. A problem frequently encountered in the analysis of categorized data concerns the independence of two methods of classification of the observed data. For example, in a survey, the responding consumers could be classified according to their sex and their preference of our product over the next competing brand, again measured by classifying them into three categories of preference. Such data is first prepared in the form of a contingency or dependency table, which helps in the investigation of dependency between the classification criteria. Now let's summarize the unit. In this unit, we have understood some situations where we can develop tests based on the chi-square distribution. We started by testing the variance of a normal population. We found that such test could be one-tailed depending on our null and the alternative hypothesis. We then developed a procedure for testing the equality of variances of two normal populations. The test statistic used in this case was the ratio of the two sample variances. This was found to have an F distribution under the null hypothesis. This procedure enabled us to test the assumption made while we developed a test procedure for testing the equality of two population means based on a small independent samples in the previous unit. We then described a multinomial experiment and found that if we have data that classify observations into k different categories, and if the conditions for the multinomial experiment are satisfied, then a test statistic called the chi-square statistic will have a chi-square distribution with specified degrees of freedom. This concept was used to develop tests concerning the goodness of fit of the observed data to any hypothesized distribution, and also to test if two criteria for classification are independent or not.
We were listening to the audiobook by the School of Management Studies IGNOU for MBA program, course code Mmpc 005, Quantitative Analysis for Managerial Applications. Voiceover by Harpreet Kaur. Edited by Savita. Program assisted by Tarannum Jahan and Jagbandhu Jana. Program produced by Dr. Manoj Kumar Singh. This program was brought to you by Electronic Media Production Center of Indira Gandhi National Open University.